Hello, welcome to session 11 in the series Analog Circuit Design using ADS. And what happens is when I'm very quickly doing something, sometimes I do writing mistake. For example, when I was deriving this gain, I forgot that I was putting input on the right hand side. So actually that was a mistake. But if just to share with you that this is a live run, I don't edit usually. I don't edit the video, so sometimes I do mistakes, so please bear with me on these mistakes. Okay, so let's get started in this session. And what I'm going to cover now is, up till now in all the amplifiers I have been dropping out what you call I've been dropping out capacitors, right? So I've been doing low frequency analysis and opening out all the capacitors. Now I'm going to do is a high frequency analysis where I will consider all the capacitors. So to start with, I would have a common source amplifier. So I would say high frequency response of common source amplifier. Okay, so now I'm not going to drop out any of the capacitors, right? So that we have all the idea of poles and zeros and stuff like that, right? So let me just first draw the small signal model for a high frequency uh, response. Okay, so I'm going to consider input resistance Rn, and the source of Rn, okay, is going to be so actually I'm assuming that the third transistor, so I'm having transistor 1 and 2 in current mirror, and then transistor number 3 is the common source gain stage. Okay, so Rn3 is the gate resistance, and this is the trace resistance of this transistor. Then you have got CGS3 here, and then you have a CGD3 here. Okay, so up till now here is okay, and then you have got GM3 here, and then you have got R. I would put here a resistance R2, and this resistance R2 is a combination, so I'll come to that. And then I would put here a capacitance C2. So let me just first clarify what is this R2 and C2, and I'm assuming that there is no body effect. So I have got drain, source is grounded, and then I have got a gate where I'm going to give in V in, right? So this node is seeing V in, and then this node is V1. So there is a division of voltage over Rn3 and CGS3, so that would be the input V1, and then this will be GM3 V1, and this output voltage is VO. Now R2, or rather I would say G2, is equal to 1 over R2, which will be equal to GDS2 plus GDS3 plus GL, right? So that is your G2. Then the next is C2. Okay, C2 will be CDB3 plus CDB2 plus CL, which is the load capacitance. So now I have defined R2 and C2 this way. Now what I'm going to do is I'm going to just write a Kirchhoff's current law at the node VO, and that would be VO times of all the connected these things. So it will be VOG2. Okay, just 1 second. So this is going to be VOG2 plus SC2, right? And then there is another one. This is CGD3 plus SCGD3. Okay, this is what is connected to VO node. Then minus the adjoining node voltage VI and the SCGD3, right? Then you have to account for the currents, right? So the currents which are flowing out are considered positive, right? So I'm going to have Vi times of Gm3. This should be equal to 0. So now with this we can establish Vo by Vi. Okay, so if I collect the terms shifted to the right hand side, I would have that Vo by Vi. So what it will be? It will be Gm, so SCGD3 and then minus of Gm3. That would be the right hand side divided by G2 plus SC2 plus SCGD3. Okay, so now I have Vo by Vi, but that's not my gain. So for my gain, I'm going to write another Kirchhoff's equation, right? And that would be at the gate node, which would be at V1, right? So I would write here V1 times of whatever is connected to V1, okay, which is basically G in 3, right? G in 3 is equal to 1 over R in 3. Okay, so G in 3 plus SCGD3 sorry, SCGD3 plus S of CGS3. Okay, minus the output node, right? So CGD3 will be there with the output node, VO times of SCGD3. Okay, and I guess, and then there is another node which is V in over here, right? So for V in there is R in, so I will have a minus V in times of G in 3 should be equal to 0. Correct? Now if I was to substitute VO from this equation, right? So I would have V1, so this is going to be quite involving, G in 3 plus, okay, V1 G in 3 plus SCGD3 plus SCGS3. VO is to be substituted. So first let me write here V in G in 3. Then we have to substitute it in terms of Vi, right? So it will be minus SCGD3 times of, so divided by this term would be there, right? Okay, I have to substitute VO in terms of Vi, right? So okay, so fine, VO in terms of Vi, right? So this will be SCGD3 minus GM3 divided by G2 plus SC2 plus SCGD3 times of Vi equal to 0, right? Now I'll collect the terms of Vi and I'll do Vi by Vin. So basically Vin goes to the right hand side and I have this term which needs to be simplified, right? So I will have this answer as G in 3 divided by this term, which is G in 3 plus SCGD3 plus SCGS3 minus of this term, which is SCGD3 times of SCGD3 minus GM3 divided by G2 plus SC2 plus SCGD3. Okay, so this will be that. Then VO by Vin would be multiplying these two terms, right? So VO by Vi into Vi by Vin. So it will be VO by Vi multiplied by Vi by Vin. So this will be equal to VO by V. This would be equal to, if I multiply these two terms, so in these two terms, uh, okay, okay, so this will be G in 3 times of the term over here, S CG, sorry, CGD3, S CGD3 minus GM3 divided by, this has to multiply, just one second. Okay, so I have to multiply with G2 SC2 SCGD3, G2 plus SC2 plus SCGD3. This thing has to be multiplying this term, which is G in 3 plus SCGD3 plus SCGS3 minus S times of CGD3 times of S of CGD3 minus GM3 divided by G2 plus SC2 plus SCGD3 and bracket close. So that would be that. Now if I was to take all the numerators and simplify, I would have VO by V in. V in will be equal to, okay, if I take minus GM3 outside, right, minus GM3 outside, right, then I would have, okay, and I am going to multiply this with R2, the denominator and the numerator. So then G2 term will go away, right, times of GM is common, right, so it will be 1 minus GM is common, right, SCGD3 by GM3, SCGD3 by GM3, and this denominator is multiplied by R2, right, and then so this will be C2R2 and this will be CGD3R2, right, so it will be 1 plus SC2R2 plus SCGD3R2. This thing has to be multiplied by this thing, so if I just solve this one, right, and in this case G2 SC2 SCGD3, okay, I'll do this, don't worry. First I will do is the following, sorry, if you see here, G2 SC2 SGD3 and this term, right, they are same, right, so if I open the bracket, I will just have a multiplication of G2 and then there will be R2 multiplied also, G2 plus SC2 plus SCGD3 times of G in plus SCGD3 plus SCGS3 minus SCGD3 times of SCGD3 minus GM3. So that will be there. And if I open the terms, so I will first take R2 in, right? And then I'm going to open the terms. And then I'm going to collect all the terms with same powers. So I'm going to have GM3 R2 1 minus SCGD3 divided by GM3, and then I am going to multiply these terms, right, so I will have some S squared terms here, and so I will have here 1, okay, so it will be 1, right, so then it will be the same term which is G in, okay, then I should also multiply by R in, Oh, because there was a G in term which I forgot here, right? Okay, so I'll be multiplying this, so this will be off. So this term, if it goes up, then there would be a multiplication with Rn3. And the same multiplication would be over here. This should be multiplied by R2 times of Rn3. So let's simplify this. Sorry. Okay. So now I'm left with G2R2 1. So R2 will go with G2 and then I'll have Rn3. Okay, Rn3 plus SC2 R2 Rn3 plus SCGD3 R2 Rn3. This thing has to be multiplied by G in 3 plus SCGD3 plus SCGS3 minus R2 are in S. So R2 are in 3 SCGD3 and there will be S square CGD3 square minus S R2 R in 3 CGD3 times of, so this minus will be plus GM3. Okay, now I have to break those terms. So it will be minus GM3 R2 1 minus SCGD3 by GM3 divided by, so if I multiply this term, this will become 1 and then it will become S times of R in 3 CGD3, right, plus S times of R in 3 CGS3 plus S times of, so second term I'm multiplying S times of C2 R2 and R in 3 will chala jayega. Then I will have this term multiplying that one, that will be S square C2 R2 R in 3 times of CGD3 okay, plus second term, right, S square times of C2 R2 R in 3 times of CGS3 plus, now I'm going to do the last term multiplying it, S R in 3 will go away with G in 3, so we'll have ref R2 CGD3 plus I would have S R2 R in CGD3 square, S square R2 R in 3 CGD3 square plus S square times of CR2 R in 3 times of, so it will be S square CGD3 CGS3, right, minus S square R1 and R2 R in 3 CGD3 square plus SR2 R in 3 CGD3 GM3. Okay, so this is quite involving, but it will simplify. So S square CGD3 square, S square R2 R in 3 CGD3 square this term cancels with that. So let me just collect the terms. So if I collect the terms, Cg3 by Gm3 divided by 1 would be common, and then let's collect the terms of S. So the terms of S have got Rn3, okay, Srn3. So Srn3, okay, R2C2 term, R2C2, just let me check the second term, R2C2 gene 3. There's no C2 term here. There is. Okay, so let's just collect the terms of Srn3. Okay, Srn3. So let's collect this term. This is first term. This will be Cgd3 plus, what's about the second term? Cgs3. Correct? Then I have another term of Srn is over here, which will be R2 Gm3 Cgd3. Okay, so this is there plus, so I have covered which terms? Let me just point. I have covered this term, I have covered this term, I have covered this term. Now let's collect S square terms. Okay, so plus S square times of, so let's look at S square terms. S square R2 Rn3, S square term R2 Rn3, S square R2 Rn3. Let's collect these terms. Okay, so this is S square R2 Rn3, so I have C2 Cgd3, C2 Cgd3 plus, let's look at another term, S square R2 Rn3, C2 Cgs3, C2 Cgs3. So do you see a pattern here? A pattern is you have a cyclic multiplication of capacitances. Okay, then let's see, another term is over here. So this is cyclic multiplication of capacitances, Cgs3 into Cgd3. Okay, so all these terms are covered. Now there are only two terms left, with its SC2 SR2, C2 plus Cgd3, right? So let's collect that term, SR2. So that will be Cgd3 plus, so SR2, Cgd3 plus C2, Cgd3 plus C2. So we have simplified this, right? Now what I'm going to do is I'm going to express this relationship. So this is gain, AV. AV is equal to minus GM3. So I'm going to write it one nice way. SCGT3. So I have just simplified this in front of you, right? This thing is divided by 1 plus S terms are in 3 terms. CGD3 plus CGS3, okay, plus plus R2 GM3 times of CGD3, correct? And then there is a SR2 term of C2 plus CGD3 plus you have S square term of multiplication of all C2 CGS3 plus CGS3 CGD3. So this is cyclic multiplication, CGD3 to C2, right? So now notice I have to get this in terms of poles and zeros. So I can write this in the form AV as AV0 times of something, right? AV0 times of something, which is going to be 1 plus the 0 S over omega z, right? So that will be the 0. 1 plus S over omega p1 plus S over omega p1 omega p2. Okay, now if omega p2 is much larger than omega p1, if omega p2 is much larger than omega p1, then I can also do a partial fraction as AV0 1 plus S over omega z divided by 1 plus S over omega p1 times of 1 plus S over omega p2. Okay, so basically this should be S square term, right? So basically the S term should give me omega p1 and S square term should be giving me omega p1 omega p2, right? So if I look at that, I can have the pole. Okay, so pole would be S equal to minus omega p1 equal to, okay, so that I will get from here, which is from the S term here, right? So this would be equal to 1 divided by R in, okay, so this will be minus 1 divided by R in 3 times of R in 3 times of this CGD3 CGS3 CGD3 CGS3 plus R2 GM R2 GM3 times of CGD3, okay, plus the RC time constant, the second term, which is R2 C2 R2 C2 plus CGS3 CGD3, not S3, CGD3. Okay, so let's see in terms of RC time constant. Okay, so the input node, okay, so look at this input node. Input node is R in 3 and I will consider the capacitances CGD3 and CGS3, okay. So okay, so the Miller capacitance, okay, so the Miller capacitance referred to the input side. This Miller capacitance referred to the input side, okay. So this Miller, C Miller in will be equal to 1 minus AV times of AV0 times of CGD3, okay. So if I consider that, I would have AV0 as GM3 R2 GM3, right? Okay, so it will be 1 plus R2 GM3 times of CGD3. Okay, so this is the Miller capacitance. So let's look at for this term. So this term is basically this plus this. So Miller capacitance, so the input node, the dominant pole is because is the RC time constant, so that will be R in 3 times of this Miller capacitor, Okay, so this is the R3, this is the RC time constant with the Miller capacitor, and the remaining is, okay, plus, so I would have to do plus of CGS3. Okay, so what it says, the first pole omega p1 is going to be the RC time constant of Miller, and that would be equal to this term, right, 1 over R in 3 times of the Miller capacitance, which is 1 plus R2 GM3 times of CGD3, plus the capacitance which is attached to this node. So if you see, all the capacitors attached to the input node, okay, is CGD3, referred to the input side as a Miller capacitor, which is minus 1 minus AV0 times of CGD3 plus CGS3 times of R in 3. So the RC time constant due to the input node gives the dominant pole. That's whole conclusion here is CGS3. So this is the dominant pole, and I am putting a minus sign because it is on the right hand side of the S plane. Oh, sorry, the left hand side of the S plane, so it's a minus time. Okay, what about WP2? Okay, so what I can do is, in this case, I would simplify this. Okay, so if I simplify this, okay, so let's take out the dominant term as just the Miller part, right? So if I consider the dominant part as the Miller part, then it will be just R2 R in 3 times of CGD3, right? And if I was to take the term S square term and S square term here, which is this one, what am I missing here? S square, I'm missing here this R2 Rn. Okay, so if I take this term and divide it by this term WP1, okay, so then I'll get WP2, right? So I will have, is that the story? Okay, one more term I'm missing here. Okay, let me see if I'm missing something. S square R2 R in 3. Just one second, bear with me. Hmm. Hmm. Right. Okay. What remains here is this R2RN GM3 CGD3. Okay. So I'm going to just do this. That what I'll be left with will be WP1 WP2. So this is 1 over. So 1 over this term multiplied by WP2, right? WP1. Okay, so R2 Rn will cancel out. Okay, so I'll be left with GM3 CGD3 divided by CGD3 CGS3 plus CGS3 C2 plus C2 CGD3. Okay, so this will be omega P2. So omega P1 is the dominant pole because of the input node, and this is dominant because of the Miller capacitor referred to the input side. What about the Miller capacitor referred to the output side? Okay, it would have a RC time constant that also, but it will be too small, so we neglected it. But this S has another term here. If you see, S has got two terms here. So this is basically the RC time constant of the output node. This is the RC time constant of the, this will give the RC time constant of the input node. So this is the output node. So let's see Miller out. Miller out is equal to C Miller out is minus AV by 1 minus AV0, correct? So times of CGD3, right? So this will be equal to R2. So this will be R2 GM3 divided by 1 plus R2 GM3 times of CGD3, which would be approximately equal to CGD3. Okay, so CGD referred to the output node will be roughly CGD3 plus C2. So the output would be the RC time constant due to, so the output would be RC time constant due to output would be equal to R2 times of CGD3 plus C2. So this is the RC time constant of the output node, right? And 1 over RC time constant is the contribution to the dominant pole, which is very small, so that's why we neglected it. So if you see here, this term we neglected. We only consider the RC time constant of the input node, right? So that RC time constant of the input node is that. So let me just look at another thing, is the 0, right? So 0 is minus WZ, okay, would be approximately equal to, so 1 over Z, right? So this would come out to be a plus number, 1 over Z, right? Omega Z. So where is that? Is this term, right? So this term, okay, is a negative, so it will be positive, so it will be on the right hand side of the S plane. It will be GM3 by CGD3. So GM3, so let me just get rid of this, so would be equal to GM3 by CGD3. Okay, so now we have all the things in our hand. Okay, so let's write them here. Poles. Okay, so we have got two poles, WP1, which has two contributions, RC time constant of the input node plus RC time constant of the output node, and 1 by that. So it will be, so I can basically forget about the output node because the capacitances are too low. So that is left with minus R in 3 times of 1 plus R2 GM3 times of CGD3. So this is the Miller capacitance on the input node plus CGS3. That's the other capacitance connected. So 1 over RC time constant of the input node is the first pole or the dominant pole. There is a small contribution from the output node, RC time constant, but it's too small. Okay, so the next thing is second pole is given by the cyclic nature of CGS. So this will be equal to minus GM3 CGD3 divided by the cyclic nature, which is CGD3 CGS3 CGS3 C2 C2 CGD3. So some of the famous books do this, just the cyclic multiplication of CGS. This is the second pole. Now there is going to be a 0 that is on the right hand side, which is basically GM3 by CGD3. Now let us see what happens. Okay, when we go to compensation, okay, you would see that if I was to If I was to increase GM3, then this WP will go down and this will go up. So if I was plotting this, what will happen is that in the Bode plot, the WP1 will move inwards while WP2 will move outwards, right? So if I was to increase GM3 of the device, okay, then the dominant pole will move in and the second pole will move out. What does it mean? It means that, so if you see, there is a whenever the pole 1 comes in, okay, so when pole 1 comes in, I have a 90-degree roll off, right? And then I have minus 20 dB per decade. Okay, now if I encounter another, if I come to the second pole, I have another minus 90 degrees, and then I would have minus 40 dB per decade roll off. Okay, so if I split the two poles by increasing GM, I move this one in and that one out, and I assume that some point this is a zero crossing in between the two poles, right? Then I would have stabilized it. Okay, I would have stabilized the stage. So let me just, I would have stabilized the common source stage. So one way of stabilizing is, technique is called split pole compensation. And what that is you increase GM3, that will cause the dominant pole to move in and the second pole to move out, and we do it to an extent that the gain crossover at 0 dB comes between the two, and now you do not have a roll off of 180 degrees, you have a roll off of 90, so you gain your phase margin, and that's how you have stabilized it. So this is called split pole compensation. Another way of doing this is I introduce a resistance with CGD3, right? So in that case, what happens is the right hand side 0 will move to the left hand side. Okay, so if that happens, what do I have? I have omega, sorry. So I would have omega z is equal to, so earlier it is GM3 by CGD3, right? Now, if I introduce a RC, okay, which I will cover later on in another model, then my pole would be CGD3, or rather C, whatever is your compensation gap. So I would not put CGD3 here. I would put C because it is different from CGD. C times 1 over GM3 minus R, which will be the RC which I introduced on the gain stage. So if there is a gain stage, one way was the split pole, other was I introduced this R and C here. Okay, so this is different from the CGD over here. So this is CGD. So that effect is swamped by these guys. So the pole would be now this one. So when this is the pole, okay, if I was to have R is equal to 1 over GM3, then what is going to happen? That the 0 would be at infinity and it will not do anything for me. But then if I keep increasing R, then this 0 will move to the left hand side. So right now it's a positive number. If you see, this is the right hand side of the S-plane because this is a positive number. But if I keep increasing R beyond 1 over GM3, then this omega z will become negative, right? So the 0 will move from the right hand side S-plane to the left hand side S-plane, right? And it would be, now you can use this to cancel your pole. So what you can do is, let's assume that you have done that, and my second pole, okay, second pole is basically GM3 CGD3 divided by CGD3 CGS3 plus CGS3 C2 plus C2 CGD3. So this is my left hand side, what you call left hand side pole 2. And if I equate this, right, to 1 over, so I'll do a minus sign here, C times of R minus 1 over GM3, that would happen. And in that case, I have to find out R. Okay, so I'll just first cancel out the terms. R would be equal to, so this term, let's cross multiply this. So R would come here, and so it will be RC minus C over GM3 should be equal to CGD3 plus CGS3 plus CGD3 CGS3 CCS2 C2 CGD3, this thing divided by GM3 CGD3. Okay, so cross multiplying, and then I have R is equal to, so C common, right? Sorry, this moves to the right hand side, so GM3. Okay, what about the C? Okay, let's bother about that. Okay, let's bother about that later. So this moves to the right. I take 1 over GM3 common times of 1 plus CGD3 CGS3. So again a typing mistake here. CGD3 CGS3 CGS3 C2 C2 CGD3. Okay, this thing is divided by GM is common, CGD3, and then C2. C comes in here. So this is going to be cancelling the second pole. So once you cancel the second pole, what's going to happen? If you introduce a pole and a 0, then the phase roll off minus 90 plus 90 is cancelled, right? But you still have got what you call 40 dB per decade of roll off, right? Because one would be 20 because of the 0, other would be 20 because of the second pole. So the roll off there would be, total roll off will be minus 60 dB per decade, right? So when you cancel the second pole with a 0, okay, this will happen when R is equal to this number. R is equal to this number. Let's simplify. CGD3 common, so that will be CGS3 plus CG3 common C2 plus C2 CGS3, right, divided by CGD3, and this whole thing is divided by C. Okay, so this is where your second pole will cancel out, and this is what I did when I kept on increasing R, right? I was first, so I cancel the, so I can move the 0 to infinity, and then I introduce in the left hand side of the S plane and cancel the second pole. If I still keep increasing R, I'll be introducing the 0 between the first pole and second. So if you see the response, what will happen is that the phase will have a 90-degree roll off, right? And then the phase, that 90-degree would be cancelled because of the 0. So omega p1 come here, and then there is omega z coming in here, and then again there will be 90-degree roll off. So that will be omega p2. So if you keep on increasing, so this is the phase response. So if you keep on increasing R, you will introduce the 0 between pole 1 and pole 2, and this will cause the phase to roll off 90 because of pole 1, and then plus 90 because of 0, and then again 90 minus 90 because of pole 2. So if you see a typical response with compensation, this will happen with op amp also, and this will also happen with common source. So So this is called lead compensation, where you are utilizing the zero which is on the right hand side. So this is the zero on the right hand side. You are introducing that zero first to the infinity. If you keep increasing r, it will move to the left hand side. Then you can cancel the second pole. That way also you can do the compensation, because that 90-degree roll off will not come, and the gain will roll off to zero. Or if you keep increasing r, you will introduce this between pole 1 and pole 2, and you will have more phase margin, because in between P1 and P2 you will cause the gain to roll to zero, right? So between P1 and P2, if you cause the gain to roll to zero, right, so you will have this kind of phase margin. So if you look at the op amp compensation, right, so if you look at the op amp compensation, which I'll just open, you will see the similar response, uh, response of a op amp. Okay, sorry about this. So you see here, this is what is happening over here, right? So this blue one is this red one you see here. So this 90-degree over here is because of this pole P1, and then there is a zero which was introduced here, which caused this to be flat. So that became flat, minus 90 plus 90, and then the second pole came in here, that will be minus 90 again. Okay, so the blue one is telling you here the phase, and which is over here as the red one, and this is what the gain is doing. So before you hit the second pole, you want to get the crossover. Okay, so this is called lead compensation. Okay, and if you were to increase GM, what you will do is the two poles you will move apart. One will move in, other will move out, and you will cause the what you call, you will cause the just a second. Okay, so you will cause the gain to die to zero between the two poles. So this is called split pole compensation technique. Okay, so we have two compensation techniques which we have seen with a common source. One is the increasing the GM causes the split pole compensation, and introducing RC causes what you call the lead compensation. And this is an example of lead compensation. You can see theoretical and simulation will stand together, and this is because this has been done in an op amp, but I'll show you. It's the same thing as a common source, because op amp also has a common source, right? So let me just show you that. Okay, so over here you see that this is a common source, this is a RC. Then RC is doing this stuff which I have mathematically explained over here. You have introduced a zero between pole 1 and pole 2. So basically this covers the basics of common source high frequency response, along with the two compensation techniques, which is split pole and lead compensation. Thanks a lot.